I want to talk today about one of the most important principles in chemistry, and I realize I say that about everything, but they all are. Equilibrium is a very important concept in chemistry because it really is the place that chemical systems drive towards in order to reach a more low energy configuration. And Le Chatelier's principle gives us a way to understand that better, because as scientists, one of the things we do is we mess with things and then we see what happens. That's really the scientific method in a nutshell. I look at something, I have an idea about the way it works, I mess with it, and then I record my results. And then I reevaluate my thinking on it based on that. So that's what scientists do, and I feel like Le Chatelier's principle is really an illustration of that. So if you have a system at equilibrium, which if you recall is when the rate of a forward reaction is equal to the rate of a reverse reaction, and you mess with it somehow, so you disrupt it or you stress it in some way, and we'll talk about some of those features of what can do that, then that system is going to shift in such a way to where it minimizes that disruption or that stress, and it will return to a state of equilibrium. So that equilibrium may be different, it may be changed, but it's still going to be an equilibrium state where the rate of the forward reaction is equal to the rate of the reverse reaction. I like to think about this in terms of old school Jurassic Park, because Jurassic Park, you know, the whole premise is they have dinosaurs, they're all female, they can't reproduce because we have all females. And so it's kind of the whole, well, nature finds a way to change that, to evolve, to grow, if given the right stimulus. And so if you're disrupting a system, if you're making all the dinosaurs female, then the dinosaurs are going to find a way to return to equilibrium, which I guess is procreating in this. So I think about it as like Jeff Goldblum. I read it always in Jeff Goldblum's voice with his, Ian Malcolm's, the character name, that nature finds a way principle, or the Jurassic Park principle. That's what it is in my mind. That was kind of a long and rambly story, but I think of it as the Jurassic Park principle. So let's talk about stressing out a system in equilibrium then. Let's look at the Haber-Bosch process. If we have nitrogen and our hydrogen and we're reacting them together, the forward reaction there is we're reacting these two gases and we form ammonia. The reverse reaction is that the ammonia is breaking down into its component pieces, into nitrogen and hydrogen. And so both of these are occurring, and if you allow the system to have enough time and you create the right circumstances, then it's going to reach a state where the forward reaction is equal to the reverse reaction. So if I wanted to mess with this in some way, if I wanted to change the rate, anything that messes with the rate is going to mess with the equilibrium. So you mess with the rate or disrupt the rate. And kind of depending on what you do to mess with the rate, you're either going to mess with the rate of the forward reaction, you're going to mess with the rate of the reverse reaction, you may mess with the rate equally, right? It may kind of speed things up in both directions. We'll just kind of see how things go. So let's think about what we could do. Well, we said anything that's going to mess with the rate is going to be something that messes with the collision of the particles. That comes from collision theory, right? So anything that increases the collisions with my reactants or with my products in one direction or the other is going to disrupt my equilibrium. So let's talk about concentration first. We know that when we increase the concentration of our reactants, that increases the rate of the process. So if I was to increase the concentration of my nitrogen, for example, then now I have more of this hanging out. So an increase in my concentration of my reactants, if I have more of this, that's going to speed up my forward reaction. And so if it speeds up the forward reaction, it's going to shift towards the products, and we're going to make more products because we had more reactants. So then we're going to balance the scales back out. It's kind of like a teeter-totter. So if I increase my reactant concentration, that's going to shift towards the products. So it shifts right. And that's kind of the language that we use to talk about this. We say that it shifts right if we're talking about towards the products, or it shifts left if we're talking about towards the reactants. So let's say, again, with kind of concentrations, I could take away, if I have like a little hydrogen magnet, and I could take away my hydrogens and pull them out of this gaseous solution here. If I was to decrease the concentration of one of my reactants, now I have lesser of these than this, so if we're thinking about balance of everything, then these guys are going to start to make more of those. The reaction is going to shift towards the reactants in order to fill the hole that I made. So it's going to shift left. Now, just like with our equilibrium constant expressions, if we're thinking about a concentration, the only thing that's going to mess with the concentration is something that actually has a concentration. So this is only going to be for gases. So anything in the gas phase or anything that's in the aqueous or aqueous phase, because those are things that we can express as concentrations. If I was going to talk about a liquid, right? If I add more liquid, especially if it's like water or something, then it's not changing anything per se. Or if I add it to my solution, then I may be changing the volume, so that would change the concentration, but I'm changing it for everything that's in there. So there's no net change. So not liquids or solids is kind of what we're talking about. So it's really just about concentrations for gases and aqueous species in the same way that we saw for our equilibrium constants. Now, of course, we can do the same thing for products. So if I was to increase the amount of my ammonia, then it would shift towards the reactants. If I was to decrease the amount of ammonia, then it would shift to fill the hole towards the products. So we have this kind of concentration relationship. Now, the second one, again, thinking about rate, temperature is always the first thing that comes to mind. You want to speed something up, you heat it up. So with an increase in temperature, though, that's really going to depend on the nature of this reaction. Is this reaction endothermic or is it exothermic? If it's endothermic, like this one happens to be, then I have to put some heat into the system. I could think about heat as a reactant here. And so if I increase my temperature for an endothermic reaction, so it requires more energy than it produces, then the heat here is going to speed up the forward reaction. If I'm speeding up the rate of my forward reaction, I'm going to produce more products and everything's going to shift towards the product side. So we shift right. And if I was to decrease the temperature for endothermic, so if I cool things off, so I cool it down, cool it down, cool it down, and that's going to push it in the opposite direction, right? Again, we can think about heat as a reactant. If I remove some heat, if I remove a reactant, then the reaction is going to shift to fill that void. So you can kind of fill in the details then for exothermic processes. So if I have an exothermic reaction, heat would be a product. And if I increase the temperature, it's going to shift towards the reactants. And if I decrease the temperature, it's going to shift towards the products. And we'd have that balance there. So temperature is going to have an influence on the stress of a system in equilibrium, but it really depends on the energy of that reaction, the enthalpy, the delta H of that process, as to how it disrupts the system. Now, another important one, especially for a system like this one, which is a homogeneous equilibrium with all gases, is pressure. We know that pressure has more of an impact on gases because they're compressible, right? I can push them down into small spaces, I can expand them out. So pressures have more influence on gases than liquids and solids. So with pressure, if I increase the pressure, the system is going to shift to the side with a fewer number of moles of gases, which makes sense because if I have a certain number of moles on either side, if I have a fewer number of moles and I'm increasing that pressure, I want to go to the side with fewer moles that are in there. So let's take our Haber-Bosch process. For this side, for my ammonia, I have 2 moles of ammonia, right? And I can tell from my coefficient out front. So let's just call N equal 2 here. And for this side, if we take this collectively, because they are our reactants, so we can take them collectively, we have 3 moles of hydrogen, 1 mole of nitrogen, so that means total I have 4 moles of gas. So when I increase the pressure on this system, the reaction is going to shift towards the side with a fewer number of moles of gas. So this one, in this particular instance, so it shifts to fewer moles. So in this instance, we're going to shift right. And vice versa. If we remove the pressure, if we don't have as much pressure on the system, then it's going to favor the side that has the greater number of moles, or it's at least going to have more of an opportunity to favor that side, kind of depending on the other factors, depending on the temperature, depending on the concentrations. Okay, now let's think about another thing that we talked about in a past video about speeding up chemical processes. Let's talk catalysts here. I'm going to put catalyst kind of as an aside. A catalyst is something that speeds up a chemical process by lowering the activation energy that's required for the reaction to occur. And so if we're thinking about a catalyst here, this speeds up both reactions. Because if we picture that energy diagram, if we picture that hill, right, and if that catalyst provides this alternate pathway to get from reactants to products, it's going to be a lower hill whether you're coming from the reactant side to the product side or from the product side to the reactant side. So because it speeds up the overall process, then it speeds up the rate of both forward and reverse reaction. So therefore isn't going to disrupt the equilibrium, right? It's going to speed up the overall process. It's going to slightly change things about the equilibrium, but it's doing it in an equal way. It's doing it the same for both the forward and the reverse reaction. So it's not going to change anything, except it's going to get you there faster, which is the purpose of a catalyst in the first place. All right, so that's a little bit about Le Chatelier's principle. We're stressing things out. We're talking about dinosaurs and applying that to the Haber-Bosch process. So if you have questions on any of this, don't hesitate to ask. Otherwise, I'll talk to you again soon.